In this video, we will be going over Algebra 1, Lesson 9.3. This is just an overview, nothing really new. We talked about parent functions and piecewise functions in the last couple of lessons, and we're going to be looking further at functions and piecewise functions. So we learned some scenarios are continuous, meaning it's data like temperature or something that just continues on. Some is discrete, like people, for example, when people are involved, and tickets, those were examples of discrete. When we're working with equations or graphs that we know fulfill the definition of a function, or they only have one output for every one input, we use function notation. So this is an important thing. Pay attention. This basically means instead of using y for our output variable, we use f of x. Using the letter f is not a requirement, but the most often used because f stands for function. So you also might see sometimes g of x or h of x for your function notation. So what that's really saying is in the past you might have seen an equation that said y equals 2x plus 1. All they're saying is because we know that full definition of function, we're just going to write f of x equals 2x plus 1 instead. So it's really saying the same thing, it's just a different way of writing it, and it gives us a little bit of flexibility. Okay, so be sure to always identify the variables you are working with, that they can be continuous. Remember, you cannot have part of some things like people, tokens, tickets, cars to be discrete. And that's something, it's just a good overview, but most of the functions we'll be working with are continuous, many of them. To begin this lesson, we are going to look at how we model functions. So modeling functions simply refers to creating a representation, like a graph, of a real-world scenario so that you can make predictions for future inputs. And that's a lot of the reason we love math, is it helps us predict the future. So whenever you're thinking, why are we doing this? That's one of the reasons. Making these models and learning how to read these models help us learn how to look at patterns and look what things are going to happen. Some scenarios may stay consistent in their rate of change. Others may vary depending on the value of the domain. So let's look at this one. Mario runs at a constant increase of speed for the first 5 minutes he runs. Then he levels off to his normal pace of 8 miles per minute. He can maintain this pace for about 30 minutes, but then he declines until he stops at 35 minutes. So I want you to pause this video, grab a piece of paper, and draw a little graph what you think this graph is going to look like. So take just a second, pause the video. Okay, so what do you think this graph is going to look like? Well, I will show you. This is what this graph could look like. So he's increasing his speed for the first 5 minutes. So we can see 5 minutes in. So this x variable would represent minutes, and this would represent speed. So he's increasing speed for the first 5 minutes. He levels off to his normal pace of about 8 miles per minute. Okay, so he's got a constant speed. And then he can maintain this pace for about 30 minutes. So we can see 30 minutes he's going to keep that constant pace, and then he declines until he stops at 35 minutes. Okay, and so you can see this graph, how it represents that. So what might this graph look like? Well, there it is. What is the x variable representing as the independent variable? So this one is representing the time, and in this case, it's minutes. So the x variable often represents time. You'll find that a lot. Okay, what is the y variable representing? Well, it represents the speed in miles per hour that he's going. So we can see for the red part, the speed is increasing, 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 and then he just has a constant speed, and then decreasing, decreasing. Is this a continuous or a discrete graph? What do you think? Well, this one is going to be continuous. It's represented by a solid line, and we can have portions of minutes. We can have little bits of time, and so this is a continuous graph. So we're going to look at this function a little bit more. So for this section, we want to look at this continuous function. If we continue to discuss Mario's race, we can define his race with the following systems of equations. So this is a piecewise function. So what this means is we have a part of it, so 0.8x, that represents this first little part of the graph, so this red part. We can see it's 4, so it's just solid at this green part of the graph. And it's negative 0.8x plus 28 for this blue part, okay? And so we can see each portion of that is represented. However, we have to have these kind of stipulations. He's only running at 0.8x when we're between 0 and 5. And if we remember, x is in minutes, so we're really saying, okay, this is his speed, this 0.8x, that represents his speed only between 0 and 5 minutes. It's a constant of 4 miles per hour between 5 and 30. So when it equals 5 and when it's less than 30. Once he gets to 30, this new negative 0.8x plus 28 represents his speed, and that's between 30 and 35 minutes. So that's how you can kind of read that this piecewise function. Okay, let's look at these helpful hints. Sometimes when we are looking at a scenario, one equation does not completely represent it from start to finish. So this is why we use these multiple equations, this piecewise function. This means when you use 3 as the input or x value, because it is between 0 and 5, you use this equation, f of x equals 2x. If you use 12, it has to be 6x because 12 would fit in between this area, okay? So the outcome would be f of 6 right here equals 6 times 12. 6 times 12 is equal to 72. So you have to kind of use those different equations. They're only true if it's between, for example, 0 and 5 for x, for the 2x. Or for 4x, it's only true when it's equal to 5 and less than 10. So this kind of helps us know when we're using each of these equations. You'll see that x is defined for a domain that starts at 0, continues until 35. Let me close this. And so anything before 0 and after 35 is of no value because he's only running for the 35 minutes. So that represents our total domain. So between 0 and 35. Between those two values, the domain is continuous. So let's work on solving for f of x. So what is the value of f of x when x is 10? So I want you to pause this video and see if you can figure that out. What is the value of f of x when x is 10? Okay, hopefully you paused and let's look at it. So when x is 10, what we want to do is we want to see where does x fit in here. So we can see we're between 0 and 5 on this top one. We're between 5 and 30 on this middle one, and that's right where 10 is going to fit in. And that means after 10 minutes, so we know when x is 10, f of x just equals 4. So that's that time where he's just going that solid pace. So another way we could say that is f of 10 equals 4. So that means when x equals 10, the value of f, or the function, is 4. So, and this paragraph kind of explains that. 0.8x is for between 0 and 5. So I'll let you read through that. This graph is just here to kind of help you, because another way is we could even look and say, okay, where does x equal 10? Well, x equals 10 right here. And we can see when x equals 10, f would be 4. That would be the 0.104. And so that is the value. That's the value of y when x is 10. Okay, or f of x. Same f of x and y, you can kind of use those synonymously. Okay, I'm going to leave this last problem. I guess we'll just look at it together since there's not a video for this one. So section 3, practice solving functions. So when we have functions, we've learned we use this function notation, f of x. So remember, it's similar to using y. The f of x notation is just general or standard form, but it can be any letter for f. The x in f of x represents what value we will substitute into the equation of the function. So for example, let's say we're given this function f of x equals 2x plus 5. Solve when x equals 4. So all we're going to do there is we're just going to put 4 in for x and solve it. So if we look, we have 2 times 4 plus 5. 8 plus 5 equals 13. So that tells us f of 4 equals 13. We'd also know that we'd have the following coordinate point to place on the graph for 13. So if we were graphing this function, we could put that point on the graph. I'm going to leave this last one for you to try. Take the following equation and solve for x for when x equals 5, 12, and negative 2. You can check your answer. And then make sure to look through this example problem below. This is another one involving a piecewise function. Good luck with the homework.